Far from the planets beyond the bright dust of the inner system, the sun hangs in space as a quiet sphere of light. It shines against a background of near black, its disk small, yet dominant, a single star among many that sits at the centre of one planetary family. From this distance there is no clear sense of storm or change. The light seems steady without flicker. The edges of the solar disk are soft, blending into the surrounding darkness, and the overall impression is one of calm persistence. Radiation leaves the sun in every direction at once, spreading outward in a nearly perfect sphere so uniform that it appears timeless. Space around it holds almost nothing. A few grains of dust, rare atoms, and the thin stream of particles that escape the star, all immersed in the broad glow that reaches across billions of kilometers. Seen from this outer region, the sun's light travels in straight lines until it meets an object that can absorb or scatter it. Planets, small rocky fragments, ice bodies, and drifting dust all intercept some of this flow, but most of the radiation continues without interruption. The star appears constant because instruments do not easily sense the subtle changes that unfold over days, years, and decades. The sun's energy output does vary, but only by a small fraction over its main cycle, and from this vast distance that variation lies hidden inside a steady glare. As a main sequence star, one that burns hydrogen in its core over very long spans of time, the sun sits in a stage of life in which change is slow. The outer appearance reflects that stability. No large structures stand out from here. Only a circular disk of light is visible, apparently unchanged from one moment to the next. The sun fills the centre of a structure called the heliosphere, a bubble carved out of the galaxy by its light and charged particles. Within this bubble, the solar influence dominates. Radiation, magnetic fields, and streams of ions move outward from the star and set the conditions in space. Light from the surface takes about 8 minutes to reach the orbit of Earth and several hours to reach the region of the giant planets. But in all directions it continues at the same speed, crossing the bubble and eventually fading into the interstellar background. The outer boundary of this region, where the solar wind slows and meets the gas between the stars, lies so far away that the sun still appears almost unchanged when viewed from there. Distance softens details and emphasizes uniformity. Around the sun, the planets orbit in paths that remain nearly flat, forming a thin disk, compared with the great sphere of the heliosphere. In this large picture, the orbits resemble faint rings, each one held in place by gravity. The light that reaches these orbits provides the energy that shapes climates, drives atmospheric circulation, and supports chemical reactions on their surfaces and in their skies. The same light also fills the empty spaces between worlds, scattering from dust grains and gas to form a very faint background glow. All of these effects trace back to processes deep inside the star, but those internal processes remain invisible from this distance. The only visible sign is the constant brightness of the disk and the steady flow of energy that reaches every orbit in turn. The sun's outer boundary, as seen in visible light, is called the photosphere. From this outer vantage point it appears smooth without fine texture. The limb, the apparent edge of the disk, shows a gentle darkening compared with the centre, a result of the way light passes through different depths of the solar atmosphere. This limb darkening is subtle, and from far away it appears as a small change in tone rather than a strong feature. There are no obvious sharp edges or shadows. The star looks like a continuous surface even though it is made of hot gas. Its colour, a soft white in the vacuum of space, comes from the broad range of wavelengths it emits, with most of the energy in the visible part of the spectrum. Viewed across many wavelengths beyond visible light, the sun's outer shape remains round and regular. In ultraviolet light, in X-ray bands, and in radio frequencies, the disk presents almost the same outline, although details of brightness change with wavelength. Instruments that can sense these different bands reveal brighter patches and darker zones, but the global geometry stays the same. The star's gravity keeps the plasma bound in a roughly spherical form, and rotation is slow enough that the shape does not flatten much at the poles. For long stretches of time, the Sun would look nearly identical in silhouette, even as internal processes slowly alter its structure on scales of hundreds of millions of years. In this outer region of space, measurements show that the total energy arriving from the Sun remains remarkably stable. Detectors on spacecraft record only small fluctuations in total solar irradiance, the integrated power across all wavelengths. These fluctuations relate to changes in surface magnetism and the presence or absence of darker and brighter regions, but they amount to less than a few parts in 100. For planets and smaller bodies, this stability is important because it means that the long-term energy input from the star remains nearly constant over human timescales. Over much longer spans, as hydrogen gradually fuses into helium in the core, the average output of the star does increase, but that change unfolds slowly compared with the shorter cycles that shape activity at the surface. From this distant perspective, no trace appears of the field lines, currents and flows that run through the solar atmosphere. The Sun may be described as quiet, even though that quiet face hides a continuous transport of energy from the core to the surface and onward into space. Photons created in the dense interior scatter many times before reaching the photosphere, yet the flow of energy at the boundary appears smooth. The star holds itself in balance with gravity, drawing matter inward, and pressure from hot gas and radiation pushing outward. In this phase, the forces match so well that the radius and average brightness remain nearly steady, and from the outer edge of the heliosphere, the star seems unchanged from one orbit to the next. From the same distant vantage point, the Sun is not only a source of light, but also an example of long-lasting balance. It exists as a main sequence star, a stage in stellar life where inward pull and outward push reach a steady match. Gravity draws every particle of plasma toward the center, trying to compress the gas into a smaller volume. At the same time, energy released deep inside the star heats the plasma and creates pressure that resists this collapse. This condition, called hydrostatic equilibrium, holds through almost every layer of the Sun. At each depth, the inward force of gravity is balanced by the outward pressure of hot gas and radiation. Because these forces match over long periods, the Sun maintains a nearly constant size and average brightness, even while the processes that sustain it continue at every moment. In the core, hydrogen nuclei fuse into helium, releasing energy in the form of high-energy photons and kinetic motion. Gravity compresses the core to high density and high temperature conditions necessary for nuclear fusion to proceed at a stable rate. If the core were to cool and fusion slowed, gravity would gain ground, compressing the gas further, which would raise the temperature and bring the fusion rate back up. If fusion ran too quickly and produced excessive pressure, the core would expand, slightly cool, and reduce the fusion rate. In this way, the star self-adjusts. The balance is not the result of any intent, but of basic physical laws that tie pressure, temperature, and density together under gravity. This feedback keeps the Sun's core in a narrow range of conditions where hydrogen burning continues steadily for billions of years. The energy produced in the core does not escape at once. Photons scatter countless times off electrons and ions in the dense interior, walking outward over long time scales. During this slow journey, energy passes from the core into the surrounding radiative zone, where it moves mainly by radiation rather than bulk motion of gas. Even here, hydrostatic equilibrium holds. At each radius, the weight of the layer above is supported by the pressure of the hot gas and radiation below. If any region were to lose pressure, the overlying material would compress it, heating it and restoring the balance. If any region became overpressured, it would expand, slightly cool, and settle back into equilibrium. The result is a star that behaves like a stable layered structure rather than a system that pulses wildly. Although the Sun appears unchanging from the outside, this equilibrium is dynamic. Particles in the plasma move at high speeds, collisions happen frequently, and fusion transforms matter at the core into new elements. Yet when averaged over large volumes and long time scales, the forces at each level remain closely matched. The persistent equilibrium of the star allows orbits, climates, and long-term planetary processes to develop under a relatively constant flow of energy. In the present phase of its life, the Sun is about halfway through its hydrogen burning stage, and its output changes only slightly over tens of millions of years. This slow evolution contrasts with later stages in stellar life, when equilibrium will be broken and the star will change more rapidly, but those stages lie far in the future compared with human timescales. From the outer layers inward, the effect of this balance appears in the regularity of the photosphere. The visible surface does not collapse inward or expand outward on short cycles, because the pressure from below always responds to any local change. Small variations in magnetic fields do alter local brightness and structure, yet the overall radius remains essentially fixed. Gravity acting on the Sun's mass sets the scale of the star, while the rate of fusion in the core adjusts to that scale. The energy production rate is such that the outward pressure supports the mass without driving global expansion. This relation between mass and energy output places the Sun along a well-studied relation between mass and luminosity for main sequence stars, and in that position it behaves as a stable engine converting mass into radiation at a steady pace. The Sun's balance also extends to its rotation. The star spins once roughly every few weeks at the equator, a rate slow enough that centrifugal forces remain small compared with gravity. The star therefore stays nearly spherical. Slight differences in rotation speed between equator and higher latitudes create shear in the outer layers but do not distort the overall shape noticeably. This differential rotation does, however, influence the magnetic field, and will later contribute to activity at the surface and in the corona. For now, as the description remains focused on balance rotation, simply adds a gentle global motion that does not disrupt the underlying equilibrium between gravity and pressure. Thermal balance accompanies mechanical balance. The energy produced in the core equals over long averages the energy radiated away from the photosphere and corona into space. If the core produced more energy than the surface could radiate, the star would heat and expand until the radiative losses matched production. If it produced less, the star would cool and contract until losses decreased. In the Sun's current state, this energy balance is close, so the global temperature structure evolves slowly. The core gradually warms as helium accumulates, which in turn causes a gradual rise in luminosity, but this change is smooth. On the scale of millennia, centuries, or even decades, the Sun's total energy output appears nearly fixed. In this way, the Sun stands as a star in balance both in its interior and in its outward appearance. Gravity, pressure, radiation, and rotation all contribute to a structure that stays close to steady state, while still allowing subtle variation. These conditions set the backdrop against which other processes will later emerge, including the magnetic cycle and the changes that lead towards solar maximum. For now, the focus remains on this broad equilibrium, the quiet framework that allows the star to shine with such steady power across the heliosphere. Beneath the visible surface of the Sun, matter and energy arrange themselves in layers that differ in temperature, density, and the way energy moves. The bright disk that instruments see in ordinary light marks the photosphere, a relatively thin shell, from which most visible photons last interact with matter before they travel outward into space. Below this thin surface, the gas becomes denser and hotter, and radiation no longer moves freely in straight paths. Instead, the interior is arranged as a series of zones, each one shaped by the balance of gravity, pressure, and the efficiency of different transport processes. From the photosphere inward, the star changes from a region where light escapes directly to zones where light is scattered many times, and finally to a central core where nuclear reactions maintain the entire structure. Just beneath the photosphere lies the upper part of the convective zone. In this region, energy is carried not mainly by radiation, but by the motion of gas itself. Hot plasma from deeper layers becomes buoyant and rises, while cooler plasma near the surface loses heat and sinks. This process repeats on many scales, forming patterns known as granulation when seen at high resolution in visible light. Each bright granule marks a rising column of hot gas, while darker lanes mark regions where cooler gas descends. The convective zone extends through a large fraction of the Sun's outer radius. Its depth is inferred from helioseismology, the study of sound waves that travel through the star and slightly modulate surface brightness and motion. Measurements show that acoustic waves change speed at different depths, revealing where convective motions give way to radiative transport deeper inside. Convection arises because the temperature gradient in this region is steep enough that radiation alone cannot carry the full energy flux outward. When a parcel of gas rises and expands, it cools, but not quickly enough to lose its buoyancy before it reaches higher layers. This behavior leads to large-scale overturning motions that mix the outer third of the Sun by radius. In these layers, the plasma is partially ionized, and changes in ionization state as gas rises and falls affect how efficiently it can radiate energy. The convective motions also interact with magnetic fields, stretching and twisting them, and helping to shape magnetic structures that will later emerge at the surface. Even so, at each depth within this zone, the local balance of gravity and pressure still holds. Convection adds motion and mixing, but does not break hydrostatic equilibrium. Deeper down, at a certain radius, conditions change. The density increases, the temperature rises, and radiation becomes a more effective carrier of energy than bulk motion. Below this boundary lies the radiative zone. Here, photons generated in the core or scattered inward from above travel outward, primarily by repeated absorption and re-emission, rather than being carried by rising and sinking gas. The plasma is fully ionized, and the opacity which measures how strongly matter interacts with radiation depends on the arrangement of ions and electrons. In the radiative zone, the temperature gradient is shallow enough that a parcel of gas displaced upward or downward quickly exchanges energy with its surroundings and returns to its original level, so large convective cells do not develop. In the radiative interior, photons follow a random walk. A photon may travel a short distance before being absorbed by an ion, which then emits another photon in a new direction. Over countless interactions, the net flow of energy moves outward, but the path of an individual photon is complex. Estimates based on models indicate that the time for energy created in the core to diffuse through the radiative zone can be on the order of hundreds of thousands of years. During this slow journey, energy gradually shifts from very high energy, gamma-ray photons, to lower energy photons in the X-ray ultraviolet, and visible ranges as scattering and absorption redistribute it. Even though the microscopic processes are intricate, the macroscopic result is a smooth outward flow that matches the energy production in the core and the energy loss at the surface. At the center of the Sun lies the core, the region where nuclear fusion takes place. Here, temperatures reach roughly 15 million degrees Celsius, and densities are high enough that hydrogen nuclei collide with sufficient frequency and energy to overcome their mutual electric repulsion. The dominant process in a star of solar mass is the proton-proton chain, in which hydrogen nuclei merge through several steps to form helium-releasing energy at each stage. This energy appears as kinetic motion of particles and gamma-ray photons. The core occupies only a small fraction of the Sun's radius, but contains a significant fraction of its mass. In this region, the balance between gravity and pressure is most critical because any significant change in fusion rate would alter the pressure and lead to contraction or expansion until a new equilibrium is reached. Chemical composition changes over time within the core. As hydrogen fuses into helium, the mean molecular weight increases, which affects the pressure and temperature structure. The core slowly contracts and heats as helium accumulates, and the overall luminosity of the Sun increases gradually on timescales of hundreds of millions of years. This slow evolution does not disturb the layered structure as described, but it does mean that the present configuration is one frame in a longer sequence of internal states. Observations of solar oscillations, together with theoretical models, give constraints on the current core conditions such as sound speed and density profile, and these constraints match well with the picture of a hydrogen-burning core surrounded by radiative and convective shells. Between the radiative zone and the convective zone lies a thin region often called the tachocline, where the mode of energy transport changes and where differential rotation shifts in pattern. In this layer, shear between the more rigid rotation of the radiative interior and the latitude-dependent rotation of the convective zone introduces strong gradients in angular velocity. These gradients are thought to play an important role in amplifying and organizing magnetic fields, although the detailed processes remain under study. The tachocline is not directly visible, but its presence is inferred from how oscillations propagate and from the patterns of surface rotation. Its existence marks an important structural transition within the Sun, a boundary where different forms of motion and transport meet. Returning outward from the core, one can think of the Sun as a series of nested shells, a central fusion region, a thick radiative mantle, an outer convective envelope, and finally the thin photospheric surface from which most light escapes. Each shell has its own typical temperatures, densities, and dominant physical processes, yet all cooperate to maintain the global balance described earlier. At any given moment, countless photons are scattered, ions are colliding, and plasma motions are reshaping local magnetic fields. But when averaged over time and space, the structure remains steady. The layered interior provides the context for later phenomena that appear at the surface, including patterns of brightness flows and other forms of activity that arise from the interaction of these internal zones. At the outer boundary of the Sun's body, where light begins its final relatively unimpeded journey into space, lies the photosphere. This layer is not a solid surface, but a thin shell of gas only a few hundred kilometers deep, a small fraction of the star's radius. It is defined as the region from which the majority of visible light escapes. Above it, the gas becomes transparent to most wavelengths of visible radiation. Below it, the gas is dense and opaque. From far away, the photosphere appears smooth and featureless, a uniform field of brightness. When examined more closely with sensitive instruments, it reveals that the surface is made of constantly changing patterns shaped by the motion of hot plasma rising and cooler plasma sinking just beneath this layer. The average temperature in the photosphere is around 5,800 degrees Celsius. At this temperature, hydrogen and helium are mostly ionized, and many heavier elements retain some electrons, giving rise to a rich set of absorption lines in the spectrum. When light from the hotter underlying layers passes through the photosphere atoms and ions, they're absorbed specific wavelengths, leaving dark lines in the otherwise continuous distribution. These spectral lines reveal the chemical composition, temperature, and motion of the gas. Small shifts in their positions show whether gas is moving toward or away from the observer, allowing the measurement of flows on the surface. This layer, although thin, holds much of the information that instruments use to understand conditions in the Sun's atmosphere and upper interior. Viewed at high resolution, the photosphere displays a pattern called granulation. Granulation consists of many small bright cells, each typically a few hundred to 1,000 kilometers across, separated by darker lanes. Each bright cell marks a location where hot plasma from deeper in the convection zone rises toward the surface. As the gas reaches the photosphere, it radiates energy into space and cools. Cooler gas becomes denser and less buoyant, so it sinks back down in the darker lanes that outline the granules. The life of a typical granule is short, on the order of several minutes, after which it breaks apart and is replaced by new rising cells. This pattern covers the entire visible disk, forming a carpet of small, constantly evolving structures. The granules behave in a way that reflects the underlying convective motions. Rising gas in the center of a cell moves upward and slightly outward, while descending gas in the lanes flows downward and inward toward deeper layers. The speeds in these flows reach several kilometers per second in the most active regions. Despite this motion, the photosphere does not become chaotic at large scales, because the convective patterns repeat and overlap in a statistically steady way. Over time, granules merge, split and rearrange, but the overall texture remains similar. Observations show that superimposed on the small granules there are larger patterns, sometimes called supergranules, with sizes of tens of thousands of kilometers and lifetimes of about a day. These larger cells also trace horizontal flows and likely connect to deeper layers of the convection zone. The brightness across the solar disk is not completely uniform. The center appears slightly brighter than the edge, a phenomenon called limb darkening. Limb darkening arises because lines of sight near the center of the disk penetrate deeper into the photosphere, reaching hotter gas, while lines of sight near the limb travel through shallower, cooler layers. Since hotter gas emits more light, the centre appears brighter. This gradual change in brightness provides another way to infer the vertical temperature structure in the photosphere. Models that reproduce the observed limb darkening help constrain the temperature gradient and opacity in this region, tying surface observations back to the internal structure described earlier. Sound waves also travel through the photosphere. The convective motions beneath the surface generate pressure waves that bounce around inside the sun, setting up standing patterns. These waves cause small oscillations in the photosphere, with parts of the surface moving in and out by a few meters and changing brightness slightly over minutes. Sensitive instruments measure these oscillations by tracking Doppler shifts and intensity variations, a technique known as helioseismology. The frequencies and spatial patterns of the waves depend on the conditions inside the sun, so by analysing them, researchers can infer properties of the internal structure, such as sound speed and rotation, as a function of depth. Thus, the photosphere serves as a visible membrane through which information about the interior becomes accessible. Magnetic fields also leave signatures in the photosphere. The sun's plasma conducts electricity, so moving charges generate and carry magnetic fields. In the photosphere, these fields tend to concentrate in the darker lanes between granules, where descending flows draw field lines together. In regions where magnetic field strength becomes high, the gas pressure adjusts and the local temperature and brightness can differ from the surroundings. Bright regions called faculae often appear near the limb associated with strong magnetic fields. Darker, cooler patches form where concentrated magnetic flux inhibits convection. These larger long-lived structures will later be recognized as sunspots in more active phases of the solar cycle. But even in quieter conditions, smaller magnetic elements thread the photosphere. Their presence alters line shapes in the spectrum through effects such as Zeeman splitting, allowing the measurement of field strength and orientation. Although the photosphere is where most visible light emerges, it is not a sharp boundary. The gas density decreases with height, and the probability that a photon escapes without further interaction increases gradually with altitude. Different wavelengths form at slightly different depths since opacity depends on frequency and composition. Shorter wavelength photons in the blue and ultraviolet can be absorbed and scattered differently from red or infrared photons, so they originate on average in different layers. This depth dependence allows multi-wavelength observations to probe slightly different heights in the photosphere, and the layers just above it building a vertical profile of temperature and motion. Energy balance in the photosphere connects directly to the deeper convection zone. The amount of energy passing through each square meter of surface per unit time must match the energy delivered from below by convective flows. If in any region the outgoing radiation were to exceed the incoming energy, the gas there would cool, increasing its density and adjusting the local flow until the flux matched again. Conversely, if the surface radiated too little, the gas would warm and expand. Over large scales and long times, these adjustments keep the radiative output of the photosphere closely matched to the internal energy generation. Short-term variations do occur, especially where magnetic fields alter convection, but the global average remains nearly constant. At the small scales of granules and magnetic concentrations, the photosphere is an active environment. Temperatures, densities, and velocities vary from cell to cell, and magnetic fields wind through the pattern. Yet when viewed from greater distance or averaged over time, this layer functions as a thin radiating shell that converts the deeper energy flows into the light that fills the heliosphere. It forms the visible face of the sun, the interface between the hidden interior and the more rarefied layers above that will be encountered next. Above the photosphere, where the gas becomes more transparent to visible light, lies the chromosphere, a thinner and more irregular layer of the sun's atmosphere. It is less dense than the photosphere by many orders of magnitude, yet it still contains enough material to influence how energy moves outward. In ordinary visible light, the chromosphere is faint, because the bright photosphere beneath it dominates the view, but in specific wavelengths, especially in the red light of hydrogen emission, and in ultraviolet bands it becomes more apparent. When observed in these bands, the chromosphere appears as a layer a few thousand kilometers thick, structured by magnetic fields and shaped by waves and flows that propagate upward from the photosphere. Temperatures in this region are higher than at the top of the photosphere, rising from values of a few thousand degrees Celsius near the base to tens of thousands of degrees Celsius at greater heights. This rise in temperature with altitude marks the beginning of behavior that differs from typical planetary atmospheres. The chromosphere is not smooth. It contains spicules, which are narrow jet-like structures of plasma that extend upward for thousands of kilometers and persist for minutes before fading and being replaced by others. These features trace magnetic field lines that emerge from the photosphere and guide the motion of ionized gas. In addition to spicules, there are fibrils and mottled patterns that shift over time. Waves generated in the convective layers below can propagate into the chromosphere, where they may dissipate and deposit energy. Shock waves from these upward-travelling disturbances contribute to heating the gas, although the exact balance between different mechanisms remains an area of study. The chromosphere therefore acts as both a conduit and a filter for energy, passing from dense layers to the more rarefied regions above. At the top of the chromosphere lies a narrow transition region, where temperature increases rapidly over a short distance. In this interface, gas changes from tens of thousands of degrees Celsius to hundreds of thousands of degrees Celsius. Density drops sharply, and the plasma becomes more fully ionized. Radiation from this region is strongest in extreme ultraviolet wavelengths, which can be detected by instruments on spacecraft. The thinness of the transition region means it does not contribute much to the total mass of the solar atmosphere, but it is crucial in setting conditions for the corona above. In this layer, conduction along magnetic field lines and radiative losses both play important roles, and the balance between them helps determine how heat is distributed. Beyond the transition region lies the corona, the Sun's outer atmosphere. The corona extends outward for many solar radii and merges gradually into the solar wind. It is composed of very hot, very low-density plasma, with temperatures of the order of 1 million degrees Celsius, or more depending on location and activity level. Despite these high temperatures, the total energy content per unit volume is low because the density is so small. The corona is best observed in ultraviolet and X-ray wavelengths, where the hot plasma emits strongly, and during total solar eclipses when the bright photosphere is blocked and the faint coronal glow becomes visible as a diffuse envelope around the darkened disk. The corona is structured by magnetic fields. In regions where magnetic field lines close back onto the sun, loops of hot plasma arch above the surface, tracing out the field. These loops can span tens of thousands of kilometers and persist for hours or days. In other regions, magnetic fields open outward into space, allowing plasma to flow along them and form the roots of the solar wind. Large-scale features called streamers and holes appear in coronal images marking zones where field geometry differs. Coronal streamers are bright, elongated regions where closed and open field lines interact, while coronal holes are darker regions where open field lines dominate, and temperatures and densities can be lower. These structures rotate with the sun and evolve on timescales of days to months. One of the central questions about the corona concerns its high temperature. The underlying photosphere is much cooler, and simple conduction would tend to move heat downward rather than upward. Yet the corona remains at temperatures far higher than the visible surface. Several processes are thought to contribute to this heating. Waves generated in the convection zone and photosphere may travel upward along magnetic field lines and dissipate in the corona, depositing energy. Small-scale reconnection events where magnetic field lines break and rejoin in new configurations can release stored magnetic energy as heat. These events can be frequent and subtle, adding energy in many small increments rather than in large bursts. The relative importance of these mechanisms varies with location and time and remains an active field of research. Radiation from the corona affects the surrounding space environment. Ultraviolet and X-ray emissions change with the amount of hot plasma and with the structure of coronal loops and open field regions. The intensity of this emission influences the upper atmospheres of planets, including their ionospheres, by adding energy and ionizing atoms and molecules there. Over longer intervals, variations in coronal output contribute to changes in the conditions through which charged particles travel in the inner heliosphere. Even when the corona appears stable in images, small changes in its density and temperature modify the spectrum and intensity of radiation that travels outward. The coronal plasma is tied to magnetic field lines, and its motion can in turn alter those fields. In regions where the field is strong and closed, plasma is confined and forms bright loops. In open field regions, plasma can expand outward, more freely feeding the solar wind. At the base of the corona in the low corona and upper chromosphere, flows may start as gentle outflows that accelerate with height. This expansion is governed by the balance between pressure gradients, gravity, and magnetic forces. As plasma moves outward along open field lines, it carries some of the sun's magnetic field into space, extending the field throughout the heliosphere. Although the corona is tenuous, its effects are far-reaching. The outward expansion of coronal plasma forms the inner part of the solar wind, a continuous flow of charged particles that fills the heliosphere. The structure of the corona therefore has direct consequences for the structure of the wind, including the existence of fast and slow streams. Fast solar wind is often associated with coronal holes, where open field lines allow more direct escape of plasma. Slower wind tends to originate near streamers and regions where field geometry is more complex. These differences lead to varying conditions in interplanetary space, as the rotating sun brings different coronal structures into alignment with a given direction. In summary, within this layer, the chromosphere transition region and corona together form the sun's outer atmosphere. Each has its own temperature density and dominant processes, but all are linked by the magnetic field and by the passage of energy from the interior to space. The chromosphere acts as an intermediary where waves and fields interact. The transition region marks a steep rise in temperature, and the corona extends this hot, magnetized environment outward into the heliosphere. From here, attention can move from these outer atmospheric layers toward the magnetic field itself and the ways it threads through the sun as a whole. Threaded through the sun's outer atmosphere and down into its interior is a magnetic field that shapes much of what happens in the chromosphere and corona. This field is generated by moving plasma, since charged particles in motion create electric currents, and currents in turn produce magnetic fields. In the sun, these currents arise mainly from flows in the convective zone and from the slow rotation of the star. The result is a magnetic structure that is not static, but continually stretched, twisted, and folded by motions beneath and above the photosphere. Although invisible to the eye, the field can be traced by its effects on plasma and by how it alters the light that emerges from the surface. Near the photosphere, magnetic fields concentrate into small bundles. Convection tends to sweep field lines toward the edges of granules where downward flows draw them together. In these lanes where gas descends, the magnetic field becomes stronger as it is compressed. This process builds a network of field concentrations on scales, from a few hundred kilometers up to many thousands of kilometers. The field is often described as a collection of loops that rise above the surface and close back down nearby, although in detail the geometry is intricate. Plasma in the chromosphere and lower corona aligns with these field lines, outlining them as fine structures that appear bright or dark in certain wavelengths. The sun does not rotate as a solid body. Equatorial regions complete a rotation in roughly 25 Earth days, while higher latitudes rotate more slowly, taking close to 30 days near the poles. This differential rotation has important effects on the magnetic field. Field lines that run from pole to pole or that have components crossing different latitudes are gradually wound around the sun by the faster motion of the equator. Over time, this shearing action converts part of the field from a pattern that points roughly from south to north, called a poloidal field, into one that wraps around the star in rings, called a toroidal field. Within the convective zone, rising and sinking motions also stretch and twist magnetic fields. As fluid elements move, they can pull field lines with them, amplifying local field strength where flows converge and weakening it where flows diverge. Small vortices in the convection pattern introduce twists in the field, while larger scale flows such as those associated with supergranulation and deeper circulation can transport magnetic flux over greater distances. The combined effect is a complex magnetic environment in which field lines are rarely straight. Instead, they wind through the plasma in loops arcs and more tangled shapes that evolve over hours, days, and longer intervals. At the boundary between the radiative interior and the convective zone in the region, often referred to as the tachocline, the change in rotational behavior contributes further to magnetic field organization. The radiative interior tends to rotate more uniformly, while the convective zone above exhibits latitude-dependent speeds. The shear at this interface can help amplify fields by stretching them in the direction of rotation. Models suggest that strong toroidal fields may be stored in or near this layer, where stable stratification resists buoyant rise until fields become strong enough to push upward. When bundles of such field rise through the convection zone, they can emerge through the photosphere as coherent magnetic structures that connect surface and corona. On the visible surface, magnetic fields of different polarities coexist in close proximity. Where opposite polarity regions meet, field lines can reconnect, changing topology and releasing magnetic energy as heat or kinetic motion in the surrounding plasma. On small scales, this kind of reconnection contributes to the continual rearrangement of the magnetic pattern known as the magnetic carpet, a dense mesh of small loops that covers much of the quiet sun. Individual elements in this network may appear and disappear on timescales of minutes to hours, carried by convective flows and altered by interactions with neighboring fields. The presence of magnetic fields modifies how gas moves in the photosphere and above. In regions of strong field, gas pressure and magnetic pressure share the task of balancing external forces. This can inhibit convection locally, leading to cooler, darker areas at the surface and hotter confined plasma higher up in loops. In weaker field regions, convection proceeds with fewer constraints and granulation patterns dominate. The combination of these regimes produces a patchwork of magnetic influences across the disk, even when the overall level of activity remains modest. Surface maps of field strength derived from polarization measurements in spectral lines show that even the so-called quiet sun hosts significant magnetic flux spread over many scales. Higher in the atmosphere, the magnetic field continues to guide plasma motion. In the chromosphere, fibrils and spicules follow field lines linking small surface concentrations to larger coronal structures. In the corona, field lines define the shapes of loops, arches, and open regions where plasma can flow outward. In closed-loop systems, plasma is confined and can be heated, leading to bright structures in ultraviolet and X-ray images. In open-field regions, plasma escapes more freely, forming part of the solar wind. Thus, the magnetic field acts as a framework that organizes the coronal plasma, connecting distant points on the surface through arches of field that span large distances. Although the sun's magnetic field is generated and maintained by flows in the interior, what is seen at and above the surface is a constantly changing pattern of field emergence, transport, concentration, and cancellation. This pattern reflects the underlying differential rotation and convection that perpetually shape the field. Over time, these processes rearrange the large-scale magnetic structure, as well as the small-scale network, setting the conditions in which larger magnetic features and events will arise as the star moves through its broader cycle of activity. Over long spans of time, the sun's magnetic field does not remain fixed in either strength or arrangement. Instead, it passes through a pattern of change that repeats with a characteristic rhythm. This pattern is known as the solar cycle. When viewed through suitable filters that reveal magnetic features, the surface does not show a uniform level of activity. There are periods when few disturbed regions appear, when the disk looks relatively quiet, and other periods when many magnetically complex areas become visible. These phases alternate in a roughly regular way, with the interval from one peak in activity to the next, averaging about 11 years. The cycle is not perfectly periodic, but its overall rhythm persists across many generations of observation. The solar cycle is most easily tracked at the photosphere by counting dark regions known as sunspots. Sunspots are places where strong magnetic fields emerge from beneath the surface and locally reduce convective heat transport, producing cooler, darker patches compared with the surrounding granulation. During the low phase of the cycle, only a few spots may appear over the course of many days, and sometimes none at all. As the cycle progresses toward its more active phase, sunspots become more numerous, larger, and more magnetically complex. They often appear in groups with pairs or clusters of opposite magnetic polarity. When their numbers reach a peak, the Sun is said to be in solar maximum. After this phase, the number of spots declines again, and the cycle moves toward a minimum. Positions of sunspots on the solar disk also change in a characteristic way over the course of a cycle. At the beginning of a new cycle, the first spots appear at mid-latitudes in both hemispheres, some distance away from the solar equator. As years pass, new groups tend to emerge at progressively lower latitudes, migrating toward the equator in a pattern that, when plotted over time, resembles overlapping bands. This behavior is often illustrated by a diagram where spots form a butterfly-shaped distribution across latitude and time. Near the end of a cycle, most remaining spots appear close to the equator, while new cycle spots begin to form again at higher latitudes with reversed magnetic polarity. The overlapping of old and new patterns marks the transition between successive cycles. Beneath these surface patterns lies a deeper magnetic process. The solar cycle involves not only a change in the number of sunspots, but also a reversal of the global magnetic field polarity. Over roughly 11 years, the large-scale field that stretches from pole to pole gradually weakens, reorganizes, and then strengthens again with opposite orientation. From a full magnetic viewpoint, the complete cycle spans about 22 years, during which the field returns to its original polarity. Differential rotation and convective motions acting on the global field described earlier help transform poloidal components into toroidal bands and back again. As the toroidal field strengthens within the Sun, concentrated bundles rise through the convection zone and emerge as active regions and sunspots. When these regions decay, their magnetic flux disperses and drifts toward the poles, contributing to the reversal of the polar fields. Measurements of the Sun's magnetism at the surface and in the corona show that the cycle is not uniform from one interval to the next. Some cycles display many spots and strong large-scale fields. Others are weaker with fewer visible active regions. The duration between maxima also varies, ranging from about 9 to about 14 years in different episodes. Over longer historical periods reconstructed from indirect evidence, there have been intervals when sunspots nearly vanish for several decades and the cycle becomes very subdued. These extended lulls suggest that the underlying dynamo process, the mechanism by which flowing plasma generates and maintains magnetic fields, can shift into different operating modes. The details of these shifts remain a subject of ongoing research, but they illustrate that the solar cycle is a flexible pattern rather than a rigid clock. The record of solar activity extends beyond the era of direct telescopic observation. Variations in the Sun's magnetic output leave traces in materials that respond to changes in high-energy particle fluxes at Earth. Certain isotopes produced in the atmosphere by cosmic rays and later stored in tree rings or ice layers vary in concentration, depending on how strongly the Sun's magnetic field deflects incoming charged particles. When solar magnetism is strong, fewer cosmic rays reach the inner system, and production of these isotopes decreases. When solar activity is low, more cosmic rays penetrate and production increases. By studying such records, researchers reconstruct aspects of the solar cycle over many centuries, confirming that the 11-year rhythm has persisted, though, with varying amplitude through long stretches of time. Within a single cycle, the rise and fall of activity are not perfectly smooth. The growth from minimum to maximum often proceeds more rapidly than the decline from maximum back to minimum. the distribution of active regions can shift between hemispheres, with one solar hemisphere sometimes leading the other in activity. Shorter-term fluctuations overlay the long trend as individual active regions emerge, evolve, and decay on timescales of days to weeks. Despite these complexities, statistical measures such as sunspot number and radio flux still exhibit a clear envelope that rises and falls in step with the cycle. Radiative output in certain wavelength bands, particularly in ultraviolet and X-rays from the corona, also changes as the cycle progresses, increasing when more hot coronal structures are present and decreasing when the corona is less structured. During the approach to solar maximum, the number of active regions increases and the global magnetic field becomes more intricate. The simple dipole pattern with opposite polarities at the two poles is overlaid by many smaller scale fields associated with sunspot groups. The polar fields weaken as flux from decaying active regions migrates poleward and cancels the previous polarity. Around the peak of the cycle, the large-scale field reorganizes and reverses, and the global configuration becomes more complex for a time. As the cycle then declines, the new polar fields strengthen, the number of active regions falls, and the structure of the field gradually simplifies again. In this way, the Sun alternates between more ordered and more tangled magnetic states on the timescale of the solar cycle. The existence of the solar cycle means that the Sun's behavior is not strictly constant on decadal scales, even though its total energy output varies only modestly. The changing magnetic field affects the distribution of sunspots, faculae, and coronal structures, altering the texture of the photosphere and corona. These changes modulate the radiation and particles that flow into the heliosphere and influence the environment around the planets. The cycle, therefore, forms a central organizing pattern for solar magnetism and activity, providing the broader temporal framework within which individual events such as flares and eruptions later occur. On the bright surface of the Sun, sunspots mark the places where magnetic fields push strongly through the photosphere and alter the usual flow of heat. In ordinary white light, they appear as dark blemishes against the surrounding granulation, yet they are not truly dark, only cooler and less bright than the nearby plasma. A typical sunspot consists of a central region called the umbra, which is the darkest part surrounded by a somewhat brighter filamented ring called the penumbra. The umbra can reach temperatures of about 4,000 degrees Celsius, while the nearby photosphere is closer to 5,800 degrees Celsius, so the contrast makes the spot stand out clearly. Sunspots can span from a few thousand kilometers across to many tens of thousands of kilometers, with the largest ones comparable in size to entire terrestrial planets. They often occur in groups where several spots of different sizes and polarity share a common magnetic origin below the surface. The formation of a sunspot begins below the photosphere in the convective zone where magnetic fields are stored and stretched. As the solar dynamo operates, toroidal magnetic fields strengthen at certain depths and latitudes. In some regions, these fields become sufficiently concentrated that their buoyancy increases. Magnetic pressure within a bundle of field lines reduces the density of the plasma there, making the structure lighter than its surroundings. Buoyant magnetic flux tubes then begin to rise through the convection zone, pushed upward by the density contrast. As they ascend, convective motions and rotation can bend and twist them, but the overall structure remains coherent enough that bundles emerge at the surface as paired regions of opposite polarity. The first sign at the photosphere may be small, short-lived features where magnetic flux breaks through. Over time, additional flux emerges and concentrated patches of field grow to form full sunspots. When a rising flux tube reaches the photosphere, it does not usually appear as a single spot at once. Instead, the tube intersects the surface along an elongated path, and plasma drains downward along the field lines, deepening the magnetic concentration. The leading end of the tube in the direction of solar rotation often forms a more compact, stronger spot, while the trailing end forms a more dispersed group of smaller spots or pores. This asymmetry, observed consistently across many sunspot groups, reflects the combined effects of rotation-convection and the orientation of the underlying magnetic torus. The pair of main polarities that results at the surface traces the path of the flux tube's emergence through the photosphere. Within a mature sunspot, the strong magnetic field alters the balance of forces. Magnetic pressure adds to gas pressure in supporting the weight of the overlying atmosphere. To maintain equilibrium, gas pressure in the spot can be lower than in the surrounding regions. Lower gas pressure means lower density, and under radiative losses, lower temperature. Convection, which normally brings hot plasma up from below, is strongly inhibited where magnetic field lines are vertical and concentrated. In the umbra field, strengths can reach several thousand Gauss, and convective motions are greatly reduced. The result is a cooler, darker core, where energy escapes mainly through radiation rather than through overturning flows. In the penumbra, where field lines are more inclined and somewhat weaker, convection is modified but not completely suppressed, leading to the filamentary structure seen in high-resolution images. The penumbra itself hosts flows that follow the inclined magnetic field lines. Bright filaments often show an inward upflowing component near their inner ends, and an outward downflowing component farther out a pattern, linked to magnetoconvection in highly inclined fields. Along these filaments, plasma can move at speeds of several kilometers per second, producing the so-called evershed flow that carries material radially outward from the umbra toward the edge of the spot. Beyond the penumbral boundary, the magnetic field fans out and merges with the more general photospheric field, and granulation resumes its usual pattern. The sharp change in brightness and structure at the edge of the penumbra marks the transition between the strongly magnetized convection, modified interior of the spot, and the surrounding convective envelope. Sunspots do not appear alone on the disk in a random fashion. In each hemisphere during a given cycle, bipolar groups show a consistent ordering of polarity, often called Hale's law. One polarity leads in the direction of rotation, and the opposite polarity trails. In the next cycle, the pattern reverses, so the leading polarity in each hemisphere switches sign, matching the flip in the global magnetic field. This regularity indicates that sunspot groups represent the visible manifestation of the deeper organized toroidal field created by the dynamo. The tilt of the line connecting the two main polarities in a group relative to the east-west direction, often described by Joy's law, tends to increase, with latitude suggesting that the emerging flux tubes are influenced by the Coriolis force as they rise. The birth and decay of sunspots follow characteristic timescales. Small pores may appear and vanish within a day, while large complex groups can persist for several weeks, or in some cases more than a month as the sun rotates. During their lifetime, spots can grow by accumulation of additional flux from below, and by coalescence of smaller elements, and later shrink as their magnetic fields disperse and reconnect with surrounding fields. The edges of spots are particularly active regions for interchange between concentrated and diffuse flux. Magnetic flux that leaves the confines of the spot is carried away by convective flows and supergranular motions spreading across the surface and contributing to the network field that covers quieter regions. The presence of sunspots alters more than just local brightness. Regions surrounding and between spots carry strong, often sheared magnetic fields that connect opposite polarity areas. These fields reach upward into the chromosphere and corona, forming low-lying loops and higher arching structures. In multi-spot groups, the coronal magnetic topology can become intricate with many loops of different lengths and orientations overlapping. While the focus here remains on the surface formation of spots, it is clear that their emergence rearranges the magnetic environment above the photosphere. The more complex the underlying spot group, the more complex the associated coronal field tends to be, as each polarity patch anchors a bundle of field lines that must connect somewhere on the surface. Despite their dark appearance, sunspot regions can be associated with increased radiative output when viewed across all wavelengths, because bright magnetic features around them, such as faculae and plages, emit strongly in certain bands. In white light images, sunspots reduce the local brightness, but the surrounding faculae, especially near the solar limb, can appear brighter than average. Over the course of the solar cycle, the net effect of many spots and faculae is a small change in the total solar irradiance. This change is measured as a fraction of a percent small compared with the overall output, but detectable with careful instrumentation. Sunspots therefore form part of a broader pattern of surface magnetism that slightly modulates the sun's energy output on decadal timescales. As magnetic flux emerges, organizes into spots and then disperses, it participates in the larger transport processes that shape the solar cycle. Flux carried toward the poles by surface flows contributes to the build-up and eventual reversal of the polar fields. Flux that cancels at polarity boundaries reduces local field strength and alters the configuration of nearby loops. Each sunspot group from its first appearance as small pores to its final dissolution into network fields represents one episode in the continual reshaping of the sun's magnetic surface. The birth of sunspots thus marks a local surface-level expression of deeper magnetic evolution within the star and prepares the ground in magnetohydrodynamic terms for the more energetic events that arise when stressed fields in and above these regions release stored energy. In and above magnetically active regions where sunspots and their surrounding fields create complex patterns, the sun sometimes releases energy in sudden bursts. These events, known as solar flares and coronal mass ejections, arise when stressed magnetic fields in the corona rearrange into a lower energy configuration. The corona, structured by loops and arcades of plasma tied to field lines, does not always maintain a simple relaxed shape. Motions at the photosphere twist shear and braid the footpoints of coronal loops over hours and days. As this happens, magnetic energy accumulates in the field, when conditions allow parts of the field restructure, rapidly converting stored magnetic energy into heat, kinetic energy, and radiation. From the perspective of the outer atmosphere, these events are brief departures from the corona's otherwise steady behavior, yet they can involve energy comparable to many millions of large volcanic eruptions on a terrestrial planet. A solar flare is a sudden brightening in the solar atmosphere seen most clearly in X-rays, ultraviolet light, and in some chromospheric lines. Flares occur when magnetic reconnection takes place in the corona. In reconnection, oppositely directed field lines are brought together, change their connectivity, and snap into a new arrangement. This process releases magnetic energy, accelerating particles and heating plasma in and near the reconnection region. In the lower corona and upper chromosphere, heated plasma emits strongly across a broad range of wavelengths. Instruments record a rapid rise in brightness that can last from minutes to hours, followed by a more gradual decay as the heated plasma cools and the region returns toward its previous state. Flares are categorized by their peak X-ray flux as measured near Earth using classes that run from small common events to large rare ones. The smallest flares release modest amounts of energy and occur frequently, while the largest can be relatively infrequent and affect large areas of the corona above sunspot groups. Regardless of class, all flares follow a general pattern, a fast impulsive phase during which particle acceleration and intense radiation occur, and a longer decay phase. During the impulsive phase, electrons and ions gain high energies and stream along magnetic field lines, depositing energy when they encounter denser plasma. This energy deposition can heat chromospheric layers, driving hot material upward in flows that fill coronal loops, a process often described as chromospheric evaporation. At the same time, the reconfigured field lines form new loop structures. Bright post-flare arcades appear as hot plasma fills these loops and cools, emitting an X-ray and extreme ultraviolet bands. As cooling continues, emission shifts toward lower energy wavelengths and the loops fade or become visible in different filters. The geometry of these loop systems provides clues about where reconnection occurred and how the magnetic topology changed. In many cases, a flare remains confined to the area above and around the active region that hosted it. In other instances, the energy release accompanies a more extensive restructuring of the corona that includes the ejection of plasma into space. Coronal mass ejections, or CMEs, are large-scale expulsions of plasma and magnetic field from the corona into the heliosphere. They often arise from regions where the magnetic field has formed a twisted or sheared configuration such as filament channels and sigmoidal arcades. In these areas, cool, dense material can be suspended in the corona along magnetic field lines, forming prominences or filaments when seen against the disk. Over time, continued shearing and twisting increase the magnetic stress. When the configuration loses stability, a portion of the field and the plasma it holds can lift off from the Sun. During a CME, a large cloud of plasma and field lines rises from the low corona and accelerates outward. In coronagraph images which block the bright disk to reveal the faint outer corona, CMEs appear as expanding structures with fronts cavities and embedded bright cores. The front marks the leading boundary of the disturbed plasma. The cavity traces the volume occupied by the erupting magnetic flux rope, and the bright core often corresponds to cooler prominence material carried along within the structure. CMEs can contain masses of solar plasma comparable to many billions of tons and can reach speeds from a few hundred to over 2,000 kilometers per second, depending on the driving forces and background conditions. The relationship between flares and CMEs is complex. Many large CMEs are associated with significant flares, indicating that both phenomena can result from a common magnetic restructuring. In such cases, the flare radiates away part of the released energy, while the CME carries away another portion, in the form of kinetic energy of the expanding plasma and changes in the magnetic field. However, flares can also occur without an accompanying CME remaining confined to the lower corona, and CMEs can occasionally happen, with only modest flare signatures. The details depend on the magnetic topology, the presence or absence of overlying fields that restrain eruption, and the distribution of plasma in the region. When a CME lifts off, it perturbs the surrounding corona and the solar wind. A fast CME can drive a shock wave ahead of it as it plows through the ambient plasma. At this shock, particles can be accelerated to high energies and spread along magnetic field lines into interplanetary space. These energetic particles may arrive at distant locations faster than the bulk CME material, since they move nearly along the field at speeds approaching a significant fraction of the speed of light. Behind the shock, the main CME body expands and evolves as it moves outward, conserving magnetic flux and interacting with the background solar wind flow. The magnetic structure of a CME is important because it carries a portion of the Sun's field into the heliosphere in a coherent package. Many CMEs contain a flux rope, a bundle of twisted field lines that maintain a relatively organized configuration as they travel. Inside this structure, plasma is confined by magnetic tension and pressure. Measurements by spacecraft that encounter CMEs in interplanetary space often detect rotations in the magnetic field direction and smooth changes in field magnitude that match the structure of such a flux rope. The orientation and polarity of the field within the CME reflect the configuration in the source region on the Sun, so each event represents a direct connection between coronal magnetism and the broader heliospheric field. Even when no clear CME is launched, active regions can produce smaller ejections and jets. These narrower events involve the expulsion of plasma along open or opening field lines near coronal holes or in regions where closed and open fields interact. Jets carry less mass and energy than large CMEs, but they contribute to the mass and momentum budget of the corona and solar wind. They also provide additional sites for magnetic reconnection and particle acceleration. Together with larger eruptions, they show that the corona is not static but continually rearranging itself as magnetic stresses build and relax. Across the surface, the frequency and strength of flares and CMEs vary with the solar cycle. During solar minimum, few active regions exist and eruptions are relatively rare. As the cycle advances toward maximum and more complex sunspot groups appear, the number of flares and CMEs increases. The most energetic events tend to occur when large magnetically intricate active regions host strong shear and twisted fields near polarity boundaries. In these locations, the conditions for reconnection and instability are more easily met and stored magnetic energy can be rapidly released. However, even in quieter times, Smaller flares and small-scale eruptions continue adding to the background level of coronal activity, for the Sun itself flares, and coronal mass ejections are part of the natural process by which magnetic energy built up through differential rotation and convection is released. Over each solar cycle, the accumulation and release of this energy reshape the corona and contribute to the slow evolution of the global field. At any given moment, the corona contains numerous loops and structures that could, under the right circumstances, participate in an eruption. The actual occurrence of a flare or CME depends on the detailed magnetic configuration and how it responds to the continual motions at and below the photosphere. From the standpoint of the star, these eruptions are intermittent episodes in an ongoing sequence of magnetic stress and relaxation that play out against the broader background of the solar cycle. From the outer corona, the Sun's influence does not stop at a static boundary. Hot ionized gas continues to expand outward, carrying magnetic fields with it, and filling interplanetary space with a continuous flow known as the solar wind. This wind consists mainly of protons and electrons with smaller fractions of heavier ions, all streaming away from the Sun at speeds of hundreds of kilometers per second. Near the orbit of Earth, typical speeds in the slow solar wind range around 400 kilometers per hour expressed as kilometers per second, while fast streams can reach roughly twice that value. As the plasma moves outward, it carries an embedded magnetic field, forming what is often called the interplanetary magnetic field. The solar wind and its magnetic field together define much of the environment through which planets travel. The solar wind originates in the corona, where high temperatures give particles enough energy to escape the Sun's gravity. In open field regions, such as coronal holes, magnetic field lines extend into space rather than closing back onto the surface. Along these open lines, plasma expands outward more freely. In these areas, the gas can accelerate to higher speeds, forming the fast component of the solar wind. In regions above streamers and more complex coronal structures, the field geometry is less straightforward and the plasma expands more slowly, forming the slow wind. The detailed mechanisms that accelerate the wind, especially in the fast component, involve a combination of thermal pressure, gradients, wave pressure from Alfvén waves, and other processes that act along field lines. The balance between these mechanisms remains an area of investigation, but the overall result is a persistent outflow that streams away from the Sun in all directions. Close to the Sun, the solar wind is still adjusting to the conditions in the corona. At some distance, the flow becomes supersonic, relative to characteristic wave speeds in the plasma. Beyond this point, information about changes further out cannot easily propagate back toward the Sun, so the wind largely follows the conditions set near its source. As the plasma accelerates, its density decreases with distance, and the magnetic field it carries weakens in strength, though its structure remains linked to the rotating star. Because the Sun spins while the wind flows outward, the embedded magnetic field does not extend straight out in radial lines. Instead, it is wrapped into a spiral pattern, with field lines curved in such a way that at a given distance they tend to form an angle with the radial direction. This pattern, shaped by constant rotation and steady outflow, is often referred to as a spiral field. The solar wind is not uniform. Fast and slow streams emerge from different coronal sources, and as the Sun rotates, these streams sweep past a given longitude in repeating patterns. Where a fast stream catches up with slower plasma ahead, the two flows interact and form regions of compression. In these interaction regions, density pressure and magnetic field strength increase, creating long-lived structures that rotate with the Sun. These co-rotating interaction regions can extend across large volumes of the heliosphere and influence conditions at a range of distances. They form part of the background structure of the wind independent of individual flares or coronal mass ejections. Embedded in the wind, the interplanetary magnetic field connects back to the Sun's surface. Each field line can be traced inward to a point in the low corona, and the pattern of connection changes as the global solar field evolves over the cycle. At solar minimum, when the global field resembles a dipole field, Lines from polar coronal holes extend far into space, and the heliospheric current sheet, a large-scale surface where the magnetic polarity changes, is relatively flat and close to the Sun's equatorial plane. As the cycle advances and the global field becomes more complex, the current sheet warps and develops a wavy structure extending above and below the equatorial plane. The solar wind flows on either side of this sheet, carrying opposite magnetic polarities in different regions. As planets orbit within this environment, they pass in and out of sectors with different field orientations. Farther out, the solar wind continues to spread, but it does not extend indefinitely with the same properties. At some large distance from the Sun, the pressure of the expanding solar wind balances the pressure of the interstellar medium, the thin gas and magnetic field that fill the space between stars. This boundary defines the outer limit of the heliosphere, a bubble carved by the solar wind in the surrounding galactic environment. Inside this bubble, the motion of charged particles, including cosmic rays, is influenced by the solar wind and the interplanetary magnetic field. Outside it, the interstellar medium dominates. Observations from distant spacecraft suggest that this transition region is not a sharp shell, but a set of layers where the solar wind slows heats and eventually merges with the ambient interstellar plasma. Closer to the Sun, where the terrestrial planets orbit, the solar wind interacts with each planetary environment in different ways. Around planets with strong intrinsic magnetic fields such as Earth, the flow is diverted around a magnetosphere, with some particles gaining entry along field lines near the poles. Around bodies without global magnetic fields such as Mars and Venus, the wind can interact more directly with upper atmospheres and ionospheres, contributing to atmospheric escape and shaping induced magnetospheres. In each case, the basic driver is the same outward flow of plasma and field from the Sun, but the local response depends on the properties of the planet and its surrounding space. At this stage, the description remains focused on the wind itself and its large-scale structure, leaving specific interactions for later sections. The variability of the solar wind reflects both the steady processes of the corona and the transient events described earlier. Even in quiet conditions, the speed density and magnetic field of the wind fluctuate over timescales of hours to days as the Sun rotates and as small-scale features form and fade. On top of this background, flares and coronal mass ejections can inject additional energy particles and field into the flow. A large coronal mass ejection travelling through the heliosphere appears as a disturbance superimposed on the underlying wind, carrying its own internal structure and altering the conditions through which it passes. These disturbances can compress the ambient plasma and magnetic field drive, shocks, and temporarily modify the configuration of the interplanetary field over wide regions. Despite this variability, the solar wind on average maintains a roughly spherically symmetric outflow, with total mass loss rates that remain small compared with the Sun's total mass. Over the star's main sequence lifetime, the amount of mass carried away by the wind is a minor fraction of its total, yet the cumulative effect on angular momentum can be significant, contributing to the gradual slowing of rotation over billions of years. As the solar wind carries away plasma tied to the magnetic field, it exerts a torque on the star. This magnetic braking process is one way in which stars like the Sun lose angular momentum over time, adjusting their rotation rates and indirectly aspects of their dynamos and cycles. Instruments on spacecraft measure the solar wind directly by sampling the plasma that streams past them. They count particles, measure their energies, and record the direction and strength of the magnetic field. From such measurements, researchers reconstruct the properties of the wind track it sources and study how it changes with distance and over the solar cycle. These in situ observations, combined with remote sensing of the corona and heliosphere, provide a picture in which the solar wind is both a continuous outflow and a carrier of the Sun's changing magnetic state. As the star moves toward and through its periods of maximum activity, the structure of the wind, the pattern of its sectors, and the frequency of disturbances in it all shift, setting the stage for the interaction with planetary environments that follows. As the solar wind flows outward from the Sun, it eventually meets the magnetic field and thin atmosphere of Earth. At the distance of Earth's orbit, the wind has become a diffuse supersonic stream of charged particles threaded by the interplanetary magnetic field. Earth carries its own dipole-shaped magnetic field, tilted slightly with respect to the planet's rotation axis, and offset modestly from the geographic centre. Where the outward-moving plasma encounters this field, the flow cannot simply pass through, as though nothing were present. Instead, the wind is deflected and slowed, forming a boundary around the planet known as the magnetosphere. This region is a cavity in the solar wind carved out by the competition between the dynamic pressure of the flowing plasma and the magnetic pressure of Earth's field. On the side facing the Sun, the magnetosphere is compressed. At a distance of several Earth radii from the planet, the solar wind is slowed abruptly in a bow shock, where the supersonic flow transitions to a slower, heated, and more turbulent state. Beyond the bow shock lies the magnetosheath, a sheath of disturbed plasma that still moves around the planetary field but no longer at the same speed or with the same ordered structure as the undisturbed solar wind. Closer in, where the pressure of Earth's magnetic field dominates the magnetopause, marks the outer boundary of the main magnetospheric cavity. Inside this boundary, the motion of charged particles is largely governed by Earth's field, rather than by the interplanetary field carried by the solar wind. The overall shape of the magnetosphere is asymmetric. On the day side, it is compressed into a blunt obstacle facing the Sun, while on the night side it is stretched into a long magnetotail that extends far downwind. Field lines that are closed near Earth form loops that emerge from one hemisphere arch through space and return to the other hemisphere. Farther from the planet on the night side field, lines are drawn out into nearly straight segments that point away from the Sun. In this tail region, plasma sheet structures and current layers separate lobes of oppositely directed magnetic field. The magnetotail stores energy carried in by the solar wind and its embedded field, and can later release part of that energy back toward the inner magnetosphere through processes of reconnection and plasma acceleration. Within the magnetosphere, charged particles follow spiral paths around magnetic field lines, while also drifting along and across them. Near the equatorial plane, trapped populations of electrons and ions form structures known as radiation belts. In these belts, particles bounce between mirror points in the northern and southern hemispheres and drift azimuthally around the planet. Closer to Earth, denser plasmas form a torus in the inner magnetosphere, while farther out the plasma sheet in the tail supplies particles that can be energized and injected toward the planet during disturbed times. Even when the solar wind is relatively steady, there is a continual exchange of energy and particles between the outer and inner regions, maintaining a dynamic but persistent configuration. The boundary between the solar wind and the magnetosphere is not completely closed. Magnetic reconnection can occur where the interplanetary magnetic field carried by the wind meets Earth's field at the magnetopause. When field lines of opposite direction are pressed together, they can break and reconnect, forming new lines that link the solar wind to the magnetosphere. This process opens a pathway through which solar wind plasma and energy can enter the magnetosphere, and through which magnetic flux can be transferred from the day side to the night side. The efficiency of this coupling depends on the orientation of the interplanetary field. When the field points in a direction opposite to Earth's day side field, reconnection at the subsolar magnetopause is more effective, and energy input into the magnetosphere increases. Magnetic flux that is opened on the day side is swept tailward by the solar wind flow, adding field lines to the lobes of the magnetotail. In the tail, further reconnection can occur in a region where oppositely directed field lines approach each other across a thin current sheet. When reconnection happens, their new closed field lines form closer to Earth, and other lines become disconnected from the planet and are carried away down the tail. The newly closed lines contract and move earthward, bringing plasma with them and injecting energy into the inner magnetosphere. This process, often referred to as magnetospheric substorm activity, leads to enhanced currents and particle precipitation in the upper atmosphere at high latitudes. Where magnetic field lines intersect Earth's upper atmosphere, charged particles can travel along them and collide with atoms and molecules in the rarefied gases there, At altitudes of around 100 to several hundred kilometers, these collisions can excite atmospheric constituents, which then emit light as they return to lower energy states. The result is auroral emission, forming characteristic ovals around each magnetic pole. From orbit, these ovals appear as rings of faint structured light encircling the polar regions. From the ground at high latitudes, they appear as diffuse bands, arcs and patches that brighten and fade as particle precipitation varies. The colours and forms depend on the species involved, the altitude of emission, and the energy of the precipitating particles. Auroral activity reflects changes in magnetospheric configuration. During quieter times, the auroral ovals remain relatively steady marking regions where a modest flux of particles continually enters the upper atmosphere. When energy input from the solar wind increases, the magnetotail becomes more active. Reconnection in the tail accelerates particles earthward along field lines that connect to the nightside polar regions. As these particles reach the atmosphere, the auroral oval brightens and expands, and dynamic structures can appear, moving equatorward and then retreating poleward as the system stores and releases energy. These changes unfold over intervals from minutes to hours, tracing how the magnetosphere responds to changes in solar wind pressure and magnetic orientation. In addition to auroral emissions, enhanced coupling between the solar wind and magnetosphere alters electric currents that flow in and around Earth. Large-scale current systems close along field lines and through the ionosphere, the ionized part of the upper atmosphere. When energy input increases, these currents strengthen, modifying the magnetic field measured at the surface. Observatories distributed around the globe record these variations as quiet patterns on most days, and as larger disturbances when coupling is stronger. Indices derived from such measurements provide quantitative descriptions of magnetospheric activity over time, mapping how the system passes between more quiescent and more disturbed states in response to changing solar wind conditions. Even during intervals that might be described as calm, the region around Earth remains in motion. Waves propagate along field lines and across plasma boundaries. Small-scale reconnection events occur at the magnetopores, and in the tail, and particles drift through the radiation belts. The magnetosphere continually adjusts its shape and internal structure to match the changing conditions of the upstream solar wind. Over days and weeks, patterns in the solar wind associated with coronal holes, stream interaction regions, and passing ejectors sweep past Earth, modulating the rate at which energy and particles enter the system. Over the slower rhythm of the solar cycle, the average level of activity changes as the sun's magnetic output waxes and wanes. Through all of this, Earth's field serves as a mediator, reshaping the solar wind flow and shielding the lower atmosphere and surface from much of the direct impact of the charged particles streaming outward from the sun. Orbiting within the flow of the solar wind and inside Earth's magnetosphere, fleets of satellites operate in an environment shaped by the sun's changing activity. Each spacecraft travels through a mixture of trapped radiation, magnetospheric plasma, and occasional disturbances carried by coronal mass ejections and fast streams. Under quiet conditions, this environment is relatively stable, and satellite systems function within expected limits. During periods when the sun is more active, especially near solar maximum, the surrounding conditions change. Enhanced fluxes of energetic particles, stronger electric fields, and compressed magnetic boundaries alter both the space plasma and the radiation levels through which satellites move. Technology in orbit responds to these changes in ways that can be measured, predicted to some degree, and mitigated, but not entirely avoided. The connection between solar activity and satellite behavior is therefore a central part of the broader picture of solar maximum. In the higher parts of the magnetosphere, particularly along orbits that pass through or near the radiation belts, energetic electrons and ions pose a constant presence. Increased solar activity can inject additional particles into these regions and change their energy distributions. As these particles strike satellite surfaces, they can charge insulating materials, building up electric potentials between different parts of the spacecraft. When the potential difference becomes large enough, a sudden discharge can occur, releasing stored charge in a brief current. Such discharges may disturb onboard electronics, causing bit flips in memory or temporary malfunctions in systems that rely on stable voltages. Shielding, grounding, and circuit design reduce the likelihood of lasting damage, yet the underlying process remains a direct consequence of the particle populations that are themselves tied to the Sun's magnetic output. At lower altitudes, where many satellites in low Earth orbit travel the upper atmosphere and ionosphere play a more prominent role. During geomagnetic disturbances, energy deposited in the upper atmosphere heats and expands it, raising the density at altitudes where satellites usually encounter thinner air. Increased density leads to increased drag. For satellites that normally experience only modest resistance, this added drag can alter their orbits measurably. Over days, orbital decay accelerates and trajectories shift. Operators track these changes and adjust orbits where possible, but the fundamental driver is the temporary expansion of the upper atmosphere caused by enhanced energy input from the solar and magnetospheric environment. Even small changes can accumulate, especially for objects without active propulsion, such as older satellites and fragments of debris. Radiation effects in satellite electronics also intensify when the Sun is active. Solar energetic particle events during which protons and heavier ions are accelerated near the Sun to high energies can send bursts of particles along interplanetary magnetic field lines that intersect or pass near Earth. When these particles reach the vicinity of satellites, they can penetrate shielding and deposit energy in sensitive components. Individual high-energy particles may cause what are called single-event effects, flipping a bit in memory or triggering a transient in a microelectronic device. In more intense events, accumulated dose can gradually degrade materials, solar cells, and detectors. Spacecraft designed for high radiation environments use hardened components and extra shielding, but even so, measurements show clear increases in radiation dose during major solar events, compared with quieter periods. Navigation and communication systems in space also interact with the disturbed environment. Signals from global navigation satellite systems travel through the ionosphere, where free electrons affect how radio waves propagate. During geomagnetic storms, electron density becomes more irregular, and structures such as patches and scintillation regions form. As signals pass through these irregularities, their phase and amplitude can fluctuate. Receivers on the ground or in other spacecraft may experience degraded accuracy or temporary loss of lock. The underlying signal remains intact at its source, but the variable medium modifies it. Careful modelling of the ionosphere and use of multiple frequencies help correct for these effects. Yet during strong disturbances, residual errors can increase beyond normal levels. Beyond space currents induced by changing magnetic fields extend their influence into technological systems on the ground. When a geomagnetic storm compresses the magnetosphere and alters the configuration of currents in the ionosphere, the magnetic field at Earth's surface changes more rapidly than usual. According to basic electromagnetic principles, time-varying magnetic fields induce electric fields in conductive materials. In the solid Earth, these induced fields drive currents through the crust and mantle. Where long-grounded conductors such as power transmission lines span large distances, the induced electric fields can push extra currents through transformers and network components. These geomagnetically induced currents add a slowly varying component to the normal alternating currents of a power grid. In most cases, systems tolerate this extra load without major consequence. But during strong storms, the induced currents can become large enough to cause saturation in transformer cores and additional heating in conductors. Saturated transformers behave less efficiently and can produce harmonics that propagate through the grid, potentially tripping protective equipment or causing voltage instabilities. Operators monitor geomagnetic conditions and system behavior to manage these risks, and many grids incorporate procedures to reduce vulnerability. Still, the physical connection remains currents in the near-space environment during a storm lead through induction to currents in man-made infrastructure many thousands of kilometers long. Long pipelines present another example of this coupling. Steel pipelines buried in the ground are often connected to cathodic protection systems to control corrosion. Geomagnetically induced electric fields can drive currents along the length of such pipelines, modifying the potentials that protection systems are designed to maintain. Over time, repeated disturbances can affect corrosion rates and monitoring data. Engineers take these influences into account when designing protection schemes, especially in high-latitude regions where storm time-induced fields can be stronger. Again, the chain of cause and effect begins with changes in the magnetosphere during solar activity and extends into the currents that flow quietly through hidden infrastructure. Radio communication systems, particularly those that rely on high-frequency bands reflected from the ionosphere, also respond to solar and geomagnetic conditions. Under normal circumstances, layers of ionized plasma in the upper atmosphere refract or reflect certain radio frequencies, allowing signals to travel beyond the horizon. During solar flares, enhanced ultraviolet and X-ray radiation from the sun increases ionization in the dayside upper atmosphere. This can lead to increased absorption of high-frequency radio waves in the lower ionosphere, creating periods when signals that normally propagate over long distances become weak or disappear along some paths. At higher latitudes, energetic particles precipitating into the atmosphere during storms can further enhance ionization in polar regions, leading to radio blackouts along routes that pass through or near the polar caps. Very low frequency and low frequency systems which can penetrate seawater and are used for specialized communication with submerged platforms respond differently. Changes in the conductivity and height of the ionosphere alter the waveguide formed between the ground and the ionosphere through which these frequencies propagate. As solar and geomagnetic activity vary, the characteristics of this waveguide shift, changing the amplitude and phase of transmitted signals. Observations of these changes have been used not only to track communication quality, but also to study the state of the upper atmosphere itself, revealing how even the lowest frequency technologies couple to solar-driven variability. Global positioning and timing systems link space-based and ground-based segments into a single functional whole. Satellites broadcast precise timing signals and orbital information, while receivers use these data to determine position and synchronize clocks. During geomagnetic disturbances, as ionospheric irregularities increase, and as satellite orbits experience enhanced drag, the relation between measured signal travel times and positions becomes more complicated. System design includes redundancy-wide satellite constellations and correction models to maintain accuracy, yet the path that signals follow remains subject to the same physical medium that responds to solar conditions. The coupling is subtle on many days and stronger during disturbed times, but it persists. All these responses, charging of satellite surfaces, orbital drag radiation effects in electronics, induced currents in power systems and pipelines, and changes in radio propagation are part of a single chain that starts with variations in the sun's magnetic and radiative output. None of them requires unusually large changes in the sun's total energy output. Instead, they arise from how the sun reorganizes its magnetic fields and particles, especially near solar maximum, and how those changes propagate through the heliosphere. Technology operating in and around Earth occupies a region where the solar wind magnetosphere, ionosphere, and solid Earth all interact. In this setting, the sun's activity is not a distant phenomenon, but a continuous background influence that shapes the environment through which signals travel, currents flow, and orbits evolve. Around the sun, a constellation of instruments watches measuring light particles and fields, so that the changing state of the star and its outflow can be followed in time. Spacecraft sit between the sun and Earth at locations where gravity and orbital motion balance orbit in paths around Earth that keep them in continuous view of the solar disk or travel closer to the star on elongated orbits that dip into the inner heliosphere. On the ground, telescopes record images and spectra from the photosphere and chromosphere through the shifting filter of Earth's atmosphere. Together, these platforms form a layered system of observation, each one sampling a different part of the Sun-Earth connection. With them, the patterns already described in the interior at the surface in the corona and in the solar wind become measurable in near real time, allowing the changing phases of the solar cycle and the growth of individual active regions to be tracked as they unfold. Near the line connecting Sun and Earth about 1.5 million kilometers sunward from the planet, a gravitational balance point hosts spacecraft that maintain a nearly constant view of the solar disk. From this location, the sun-facing instruments on long-lived observatories record the brightness and structure of the photosphere and corona in multiple wavelengths. Full-disk images in visible light show the granulation pattern and sunspots as they rotate across the face of the star. Magnetographs measure the polarization of spectral lines to infer the line-of-sight magnetic field on the surface, constructing maps of field strength and polarity that reveal where active regions emerge, grow, and decay. Ultraviolet and extreme ultraviolet telescopes capture the chromosphere and low corona, where bright loops and darker coronal holes trace the magnetic skeleton of the outer atmosphere. Coronagraphs, which block the bright disk to reveal the faint corona show streamers' plumes and the outward motion of coronal mass ejections as they lift away from the Sun. Closer to Earth, satellites in geosynchronous or low Earth orbit carry additional solar instruments. Some stare continuously at the Sun to measure total solar irradiance, integrating the energy received across all wavelengths into a single quantity that can be compared from day to day and year to year. Others focus on specific spectral bands, providing detailed time series of solar X-ray and ultraviolet flux. These time series show the sudden increases associated with flares and the slower trends that accompany the rise and fall of the solar cycle. Instruments that detect high-energy particles register the arrival of solar energetic particle events and track their intensity and energy distribution as they pass the observing point. Each record becomes part of a composite picture of how radiation and particles from the Sun change over intervals from seconds to decades. Farther inward toward the star probes follow trajectories that carry them well inside the orbit of Mercury. On these paths, they sample the solar wind and magnetic field in regions that were previously accessible only through remote sensing. As they approach perihelion, the closest point in their orbits, they measure plasma fields and waves in a regime where the solar wind is still being accelerated and where the structure of the corona transitions into the outflow. Instruments on board record the detailed shape and fluctuations of the magnetic field, the distribution of particle speeds and directions, and the spectrum of waves and turbulence in the plasma. These measurements help connect conditions observed near the Sun to those measured near Earth, tracing how structures evolve as they move outward. At the same time, remote sensing instruments on these probes image parts of the corona and photosphere from vantage points off the Sun-Earth line, adding a three-dimensional aspect to the observational network. Within the magnetosphere and just upstream of it, other spacecraft serve as monitors of the solar wind that is about to encounter Earth. At the same gravitational balance point sunward of the planet, where some solar imagers also reside, plasma and field detectors measure the local solar wind speed density, temperature, and magnetic field orientation. These upstream measurements capture the arrival of shocks driven by coronal mass ejections, the passage of fast and slow streams, and changes in the interplanetary magnetic field. Because the wind takes some tens of minutes to travel from this point to Earth, these observations provide a short lead time during which the magnetospheric response can be anticipated in broad outline. Similar instruments on spacecraft in other orbits fill in additional details recording how the solar wind and the magnetosphere interact at different locations. On the sun-facing side of Earth, ground-based observatories complement space instruments. Networks of solar telescopes distributed across longitudes monitor the photosphere and chromosphere in visible and near ultraviolet light, providing high-resolution views of sunspots, faculae filaments, and prominences. Spectrographs analyze the solar spectrum to derive velocities and line-of-sight magnetic fields over limited fields of view, revealing fine structure in active regions and quiet areas alike. Radio observatories detect emissions from the corona and from accelerated particles, tracing bursts associated with flares and eruptive events. Because they are anchored on the ground, these instruments are limited by daylight and weather, but by forming global networks, observers reduce gaps and build continuous records of many solar features. Helioseismology. The study of solar oscillations relies on precise measurements from both space and ground. Photometers and Doppler imagers record small changes in brightness and surface motion caused by acoustic waves that travel through the sun's interior. By decomposing these observations into modes with specific spatial patterns and frequencies, scientists infer the sound speed and rotation rate as functions of depth and latitude. This internal information constrains models of the convection zone, the radiative interior, and the tachocline where the dynamo is active. Changes in oscillation properties over the solar cycle reveal how the magnetic field modifies the interior structure in subtle ways. Thus, monitoring the surface becomes a means of tracking processes that cannot be seen directly, forming an inner counterpart to the imaging of outer atmospheric layers. All of these measurements feed into models that attempt to describe and to some extent forecast solar behavior. At the scale of the solar surface, magnetic maps derived from magnetograms serve as boundary conditions for models of the corona, in which magnetic field lines are extrapolated to estimate the configuration of loops, open field regions, and the routes of fast and slow wind streams. At larger scales, models of the heliospheric field use observed surface flux and simple wind prescriptions to calculate the structure of the interplanetary magnetic field and the location of the heliospheric current sheet. At the interface with Earth-coupled models of the solar wind magnetosphere, ionosphere, and upper atmosphere use upstream measurements to estimate how incoming disturbances will reshape currents, fields, and particle populations around the planet. These models are built on physical principles and are continually adjusted as new data refine their parameters. Forecasting solar activity involves different timescales and levels of detail. At the longest scales, monitoring of sunspot numbers, magnetic fields, and radiative output provides indicators of where the sun sits in its cycle, whether activity is generally increasing or decreasing, and how the polar fields which seed the next cycle are evolving. On intermediate scales of days to weeks, the growth and decay of individual active regions can be tracked as they rotate onto and across the visible disk. Complex magnetic structures near the surface and in the corona are noted for their potential to host flares or eruptions. At the shortest scales of minutes to hours, real-time measurements of X-ray flux radio bursts and sudden brightenings reveal when a flare has begun, while coronagraph images show whether an associated coronal mass ejection is moving outward and in which direction. From the evolution of its leading edge in these images, estimates of its speed and approximate arrival time at given heliocentric distances can be made. Despite the richness of these observations and models, forecasts remain probabilistic rather than certain. Magnetic fields near the surface are only partially resolved, and the coronal field cannot yet be measured directly over the full volume it occupies. The complex physics of reconnection, turbulence, and wave propagation introduces uncertainties into how stored magnetic energy will be released. Even when a coronal mass ejection is clearly visible, leaving the sun, interactions with the background solar wind can alter its speed and trajectory, and its internal magnetic structure may differ from simple expectations. As a result, predictions of when and how strongly a given event will affect a particular location in the heliosphere carry ranges rather than single values. Continued observation and modelling gradually reduce these ranges, but they do not remove them entirely. In this way, forecasting the sun's behaviour becomes an ongoing exercise in watching, measuring, and updating expectations as new data arrive. Instruments close to the sun record changes in the corona and wind near their source. Upstream monitors near Earth sample the conditions about to meet the magnetosphere and ground, and space-based observatories track responses throughout the coupled Sun-Earth system. Over the course of a solar cycle, these observations build a record of how the star's magnetic activity waxes and wanes, and how that activity shapes the near-space environment. As the sun moves toward its more active phases, the same tools that describe its present state also frame the question of how the next maximum will unfold, in terms of both the patterns on the star and the conditions throughout the surrounding heliosphere. Across the span of several years, the changing face of the Sun marks the progression from one quiet phase of its cycle toward a more active state. At the photosphere, new sunspot groups begin to appear at mid-latitudes in both hemispheres, while older cycle spots nearer the equator fade away. Magnetograms show patches of opposite polarity emerging, separating and rotating with the star. In the chromosphere and corona bright active region, loops become more common, and the number of filaments and prominences suspended in the outer atmosphere increases. Coronal images reveal that the previously simple pattern of polar coronal holes and equatorial streamers gives way to a more complex arrangement of bright and dark structures distributed over a wider range of latitudes. These gradual changes tracked over months signal that the underlying toroidal magnetic field inside the Sun is strengthening and that the star is moving toward the next solar maximum. Measurements of sunspot number taken daily and averaged over months show this trend as a steady rise from the low values characteristic of solar minimum. Short-term fluctuations occur as individual active regions appear and vanish, but the general envelope climbs until it reaches a plateau near maximum. Radio flux at certain wavelengths, which serves as a proxy for coronal density, and magnetic activity follows a similar pattern, increasing as more and larger active regions populate the disk. Ultraviolet and X-ray output from the corona also grows, reflecting the presence of hotter, more numerous loops and arcades. Together, these indices provide complementary views of the same underlying process, the buildup of magnetic complexity at and above the solar surface as the cycle advances. At high latitudes, polar magnetic fields weaken and begin to reverse. Observations of the line-of-sight field near the poles show that the dominant polarity from the previous cycle diminishes as flux carried from decaying mid-latitude active regions migrates poleward. Over time, this transported flux cancels the old polar field and then replaces it with the opposite sign. The moment of reversal does not occur everywhere at once. Instead, the field in each hemisphere passes through intervals of mixed polarity before a new coherent pattern emerges. The timing of these reversals differs between hemispheres and from cycle to cycle, but in general they occur around the time of maximum activity. Once the new polar fields have formed, they act as seeds for the next cycle's large-scale magnetic configuration, linking the current maximum to future behavior on timescales longer than a decade. In the corona, these internal changes manifest as alterations in the global magnetic structure. Near solar minimum, coronal holes at the poles dominate, and the heliospheric current sheet remains relatively flat. As the cycle progresses, additional coronal holes form at lower latitudes, streamers spread over a broader band, and the global connectivity of field lines becomes more intricate. The current sheet tilts and warps, developing a wavy shape that undulates above and below the solar equatorial plane. Solar wind measurements at various heliocentric distances register this shift as more frequent crossings between sectors of opposite magnetic polarity and as changing patterns of fast and slow streams. The wind becomes more structured with interaction regions and transient disturbances more common than in the quiet phase. The frequency of flares and coronal mass ejections increases as active regions grow larger and more magnetically complex. X-ray monitors record more frequent bursts ranging from small events that barely rise above the background to larger flares that produce rapid, sharp increases in emission. Coronagraphs observe more numerous CMEs with a wider distribution of directions and speeds. Some eruptions remain confined near the limbs and propagate away from the Sun without intersecting planetary orbits, while others travel along paths that bring them into the inner heliosphere where planets reside. The distribution of event sizes follows a broad range. Many small eruptions occur and fewer large ones, but the total rate of all kinds rises around solar maximum. These measurements show that while the Sun's total radiative output changes only modestly, its impulsive and structural activity increases significantly. Near Earth upstream, solar wind monitors detect more frequent variations in speed density and magnetic field orientation. Shocks driven by fast CMEs and by the leading edges of high-speed streams show up as sudden changes in plasma parameters. The interplanetary magnetic field changes direction more often and sometimes more abruptly, creating intervals during which coupling to Earth's magnetosphere is enhanced. In the magnetosphere and ionosphere indices derived from ground-based magnetic observations and from satellite measurements of currents and particles indicate that geomagnetic activity becomes more frequent and at times more intense. Substorms and storms occur with shorter intervals between them, and auroral ovals brighten more often and at times expand to lower latitudes than during quiet years. Despite this increase in activity, the range of possible outcomes within a given maximum remains broad. Some cycles have produced relatively moderate peaks in sunspot number and modest counts of large eruptions. Others have featured stronger maxima with many active regions and several particularly energetic events. Observations over multiple cycles show that the Sun's behavior is variable within an overall pattern. The length of the cycle, the strength of the polar fields at minimum, and the amplitude of the peak all change from one interval to the next. Models link these differences to variations in the dynamo processes operating in the interior and to the transport of magnetic flux at the surface, but details remain an active area of study. As a result, predictions of the exact number of large events or the precise strength of a given maximum include ranges reflecting uncertainty in both the Sun's internal state and its external manifestations. In practical terms, moving towards solar maximum means that the environment through which Earth and its satellites travel becomes more dynamic. Communication systems that rely on ionospheric reflection see more frequent disturbances as flares and enhanced particle precipitation alter electron densities. Power grids at high latitudes experience more intervals when geomagnetically induced currents may flow, and operators consult forecasts and real-time indices more often. Spacecraft encounter more episodes of elevated radiation, and more variations in drag. Forecast centers integrate solar and heliospheric observations into daily and weekly outlooks, highlighting intervals when conditions are expected to be quiet and those when increased vigilance is warranted. These outlooks do not imply certainty, but they frame expectations in terms of probabilities tied to current solar and solar wind measurements. Yet even at maximum, the Sun does not remain in a continuously disturbed state. Quiet intervals appear between active episodes. Large regions of the disk can rotate through a view with only small or no sunspots, even when the general level of activity is still high. The corona retains zones of relative stability alongside more dynamic structures. The solar wind continues to flow outward, and its average properties remain within ranges that have been measured over many cycles. The difference between minimum and maximum is therefore not a switch from calm to unrest, but a shift in how often and how strongly disturbances occur against a backdrop of regular outflow and radiative emission. From this perspective, readiness for the next solar maximum involves understanding these patterns rather than anticipating a singular event. Ongoing measurements of sunspot numbers, polar fields, coronal structures, and solar wind parameters describe where the Sun sits along its cycle and how quickly it is changing. Comparisons with previous cycles place current behavior in a longer context, showing where it falls among the variety of past maxima. As the Sun approaches and then moves through its peak, the same physical processes continue. Magnetic fields are generated twisted and relaxed. Plasma is heated, confined, and released, and the resulting radiation and particles move outward through the heliosphere. The progression toward maximum is in this way an intensification of familiar patterns, observed more frequently and with greater detail, rather than the onset of fundamentally new behavior. Over centuries of observation and reconstruction, the Sun's behavior reveals itself as a pattern of cycles layered on longer evolutionary changes. Daily drawings made at observatories digitized magnetograms from recent decades, and indirect records preserved in ice cores and tree rings together show that the 11-year rhythm of activity has persisted through many human generations. Maxima and minima follow one another, some strong, some weak, but the alternation continues. In each cycle, magnetic fields are generated in the interior emerge through the surface and are carried away by the solar wind. Polar fields reverse and rebuild, and the global configuration of field lines reshapes itself. Against this changing magnetic background, the total radiative output varies only slightly, while the texture of the photosphere, the brightness of the corona, and the pace of the solar wind change more noticeably. The Sun at one maximum differs in detail from the Sun at another, yet the underlying pattern of rise and decline remains recognizable. On timescales far longer than individual cycles, the star itself evolves. The core slowly converts hydrogen into helium, and the mean rate of energy production gradually increases. As a result, the Sun's average brightness rises over hundreds of millions of years, altering the long-term energy input to the planets. The solar cycle superposed on this slow trend continues to modulate magnetic fields and particle output. In this combined picture, the Sun is neither strictly constant nor wildly variable. Its magnetic layers change more quickly than its radiative structure, and both change more quickly than its overall mass and radius. From the viewpoint of planetary climates and environments, the cycle sets a repeating pattern of magnetism and plasma, while the slow evolution of luminosity sets a broader context that unfolds too gradually to be noticed within a single cycle, or even several cycles. Within a given maximum, the Sun never reaches a single sustained peak. Instead, a cluster of active years encompasses many smaller rises and falls. Active regions rotate into view, produce flares and eruptions, and then decay as the surface turns. Coronal holes form and vanish, altering the pattern of fast and slow wind streams. The heliospheric current sheet warps and relaxes. The magnetospheres of planets respond in turn, their currents and particle populations adjusting to each new combination of solar wind speed density and field orientation. Quiet intervals separate more disturbed ones, and over the span of a decade or so, the overall level of variation rises and then declines. Instruments record this progression, logging each flare onset, each coronal mass ejection, each shift in the interplanetary field, adding new entries to long series that already extend back through multiple cycles. As records lengthen, patterns emerge not only in the repeating cycle, but also in its departures from average behavior. Some eras show groups of relatively strong cycles clustered together with high peak sunspot numbers and frequent large eruptions. Other eras exhibit weaker cycles with lower maxima and fewer intense events. Extended periods of subdued activity stand out when sunspots become rare, and the magnetic field at the surface appears simpler. These intervals interpreted alongside dynamo models suggest that the processes in the interior that give rise to the cycle can operate in different modes. Flow speeds in the convection zone, flux transport at the surface, and the structure of the tachocline all influence the strength and length of cycles, and small differences in these parameters can lead to noticeable changes at the surface and in the corona. Even so, across these variations, the star continues to rotate, fuse hydrogen, and emit light and plasma into the heliosphere. Around Earth, technological systems have become part of this repeating pattern. Satellites, power networks, communication links, and navigation systems now populate the region influenced by the Sun's changing activity. Their designers and operators use the accumulated knowledge of past cycles to understand how conditions in space and in the upper atmosphere change as the Sun moves from minimum to maximum and back again. Observatories track the surface fields that seed active regions, the coronal structures that launch the solar wind and coronal mass ejections, and the solar wind conditions that precede geomagnetic storms. Models ingest these data to estimate when disturbances will reach planetary orbits and how strong their effects may be, while measurements of past events provide reference points for what has already occurred. In this way, human activity in near-Earth space and on the ground becomes one more layer responding to the Sun's repeating magnetic rhythm. Looking outward across the heliosphere, each planet experiences the same broad phases in its own way. Earth's global magnetic field and atmosphere mediate the effects of solar, maximum and minimum shaping, auroral displays, radiation belt dynamics, and upper atmospheric density. Other planets with different fields, atmospheres, and distances from the Sun respond with their own magnetospheric configurations and atmospheric changes. Yet in each case, the variation in solar wind properties and radiation over the cycle modulates local space environments. The Sun's outburst at maximum is thus not a single sudden event, but a multi-year period of enhanced magnetic activity that threads its influence through many different systems across the heliosphere. As one maximum passes and the cycle declines, sunspot numbers fall, active regions become fewer, and the corona returns to a simpler, more polar-dominated structure. The heliospheric current sheet flattens the frequency of large eruptions, decreases, and average geomagnetic activity lessens. The polar fields settle into their new orientations, storing the seeds of the next toroidal field that will give rise to the following cycle's spots. The instruments that track the rise continue to operate through the decline, preparing for the next minimum, when the surface will again appear relatively quiet in white light, even as the interior maintains the flows that will regenerate magnetic complexity. This solar maximum, with all its flares, eruptions, and changing winds, becomes one phase in this ongoing sequence, framed on one side by a preceding minimum and on the other by the gradual approach of the next. In the inner region of the heliosphere, the Sun continues to shine with steady light, while its magnetic fields move through their slow alternations. Radiation leaves the photosphere in every direction, filling the space between planets with a nearly uniform glow. The solar wind flows outward as a continuous breath of plasma, carrying the interplanetary magnetic field along its spiral paths. Against this background, the rise and fall of the solar cycle introduce gentle variations, small changes in texture at the surface of the star and in the structure of the corona and wind. At any given moment, some parts of the disk host active regions and loops, while other parts remain quiet. Across years, these details shift, yet the larger pattern of outward energy and particles persists. Around Earth, the magnetosphere holds its shape against the incoming flow, sometimes compressed, sometimes more extended, always adjusting to the current conditions in the solar wind. Field lines arch from pole to pole, guiding particles that trace out invisible paths before merging back into the broader plasma. Far above the atmosphere, satellites follow their orbits through regions of varying density and radiation, responding slowly to changes in drag and particle flux. Closer in the upper atmosphere absorbs energy from the Sun and from magnetospheric currents expanding and contracting in response to the pace of solar activity. Through these layers, signals travel, currents flow, and instruments record the quiet intervals as carefully as the disturbed ones. As the cycle advances beyond one maximum and moves toward the next minimum, the rate of change eases. Sunspot groups become less frequent and smaller. Coronal structures simplify, with polar holes regaining prominence. Solar wind conditions at Earth's orbit vary less strongly from one rotation to the next. The magnetosphere and ionosphere still respond to passing disturbances, but long stretches pass with only modest variations. Records of the cycle incorporate these quieter years, marking them as another part of the repeating pattern. In this gradual slowing of magnetic activity, the star remains the same underlying engine, maintaining hydrostatic balance in its interior and radiating energy outward at nearly constant total power. Within this steady framework, the passage of time in one cycle becomes a small segment of the star's longer life. The hydrogen-burning core continues its work, the radiative interior transports energy outward, and the convective zone turns over plasma that sustains the dynamo. Above the photosphere, chromosphere, and corona respond to the slow changes below, and to the faster variations in their own magnetic structures. The heliosphere remains filled with light and plasma, and the planets continue along their paths within it. Activity rises and falls, yet the overall presence of the Sun as a stable source of warmth and light endures across cycles and across generations.